welcome to today's webinar. The topic today is building model or construction stages. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Bastian Kuhn will be the presenter today. He works in the customer support team and he is responsible for the development of the add-ons timber design and building model. You can ask questions when you press the button with the question mark, then enter your question in that field, press send, and I will receive your question and I will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Bastian. Bastian, it's your turn.
Okay, welcome also to today's webinar from my side. Yeah, few words to the content, maybe mentioned already. I want to show you today something about construction stages, wise were the positional structural analysis, and I will show you or mention or discuss problems in a 3D calculation that can occur, and I want to do I want to show you how to solve this via the analysis in the building model add-on or the construction stages add-on. Okay, that actually is all about the content, and I directly want to jump into the program. I already opened a file. Few words to the add-ons that I want to use. I will show you construction stages analysis that's already selected here, CSA. The building model add-on, I want to use multi-layer surfaces. I will not do the design of any material, but it's probably all right to have some combination wizard and classification activated. I will show you a few elements in the concrete design and the timber design, but once again, I will not show you the design of it. So these are actually on the left side, the three add-ons I mainly want to talk about today. Okay, so there are just a few notes that I already have there, and I want to start by assigning a new background layer. Therefore, I have prepared DXF, which has the, well, I could use it automatic, but I would like to define the length, which is meter. All right, so the background layer is there, and then I can directly jump into the building model add-on. First of all, I will define the building stories that I want to have here. I want to have elevation of 3 meters each story, and I want 18 stories, 14, 15, 16, and the top one set as 0 is also 1 story. Well, just a few words to the building stories. We have this add-on will generate systems, and it is able to unify 2D position design with 3D design in it. Yeah, I think the best probably is to show that directly in the program, how it's working and how it's interrogating. Right now we cannot see that much. The floor diaphragms is an important issue. We will start with the floor diaphragm none, which is just the original stiffness that you would also have when you calculate directly in RFEM without the building model add-on. Then we have semi-rigid. Once again, I will show that directly when I've activated it and show the effects of it. Just before we come to this, it is able to calculate 2D position of floors, 3D position of walls, and do the interaction of these effects. And then we have rigid, which is quite similar to semi-rigid. Of course, it has the half word of it in it. And the difference to semi-rigid is that in semi-rigid you have the real in-shear plane stiffness of each floor, and in rigid you have an exponential high rigid stiffness. So these two are quite important, and we will probably use a lot of time for using them and showing the effects of, well, maybe just semi-rigid, but in difference to none. Without stiffness is only for load transfer and not part of this webinar today. So, okay, we will start with none. Just a few pre-words. Then we have the global settings, where we can define several effects that are also not so important. So select OK. So far, not really much has happened, but we see the elevation of 54 meters already. That's all that we have. But now that we have generated the building or defined the building stories already, we have here a drop-down menu where you can define columns, walls, vertical lines, openings, rectangle floors, and so on. And we will start with the rectangular floor. And I want to define the main CLT floor. Therefore, I'm selecting the layer thickness type. So this is activated, or this is visible because I have activated the multi-layer surface add-on. Similar to the beam panel. All these two thickness types are organized under this add-on. So this is the add-on we are starting now. There are several webinars for working with layers as well as with a beam panel. So I will go through this definition quite quickly and not lose too many words about the theory behind it. I will choose as a region Europe here. There we have several producers. As combined with the definition of the producers are coming some effects that need to be regarded. All right, so then we will choose the thickness. So the structure that I want to model today has a length of 20 meters and a width of 5 meters. So that's quite a bit, and therefore we would probably need quite a section height. I would choose 20. Now the stiffness of this structure is already defined, and there are factors. Once again, if you want to know more about these, you can take a look at the other webinars. So the layer is defined, and I can go on modeling the structure. And one interesting thing, what I have now with the building model add-on, that I can now model in, I would like to call it fly mode with it. Therefore, I will activate all stories of the building here and just use the left side of the building. And right now you see, well, one surface, but when you go a little bit out of the rendering, maybe use this, you see that all 18 stories of the structure are modeled. The center, or the gravity center of the structure, is modeled in here. And so yeah, that's all done. And I can go on modeling, for instance, the wall of the structure that would be made from concrete. As I have activated the concrete design, I will just roughly define a few reinforcement products. It's not so important in this matter, but here I would use the reinforced UP500 according to Euro for this one. Okay, actually for the rest I really don't care, as we do not do any design process. Okay, then brings us to the walls or the stiffening elements of the structure. I want to model a hybrid building made from CLT timber frame wall and concrete. And you see, okay, concrete is quite heavy, therefore the gravity set or the center of the mass is a little bit transferred into this area. So maybe try to minimize it a little bit, or maybe that's okay. Well, that's a little bit too low actually. Okay, but does not matter. So that's the walls, and now brings us to the back to the floor again. I will use the same stiffness in here. So just to have it all right. And now the columns. That's the last point I need to concentrate on. I would like to choose a section 30 by 30 centimeters. I want to have hinges at the member end of it. For the moment, hinges similar to what I have when I'm defining line hinges. I like, just for the modeling issue, to define very small rotation hinges. I can activate, deactivate them afterwards all the time, and will just put them in this queue here. All right, and I would like to skip this middle center of the column and also this, just for showing the effects of the 3D or the problems that are occurring with the sudden static approach. So you see, okay, let's maybe switch on the rendering here for this. So that's all done. The columns are here. Some may ask, why are the columns do not have a hinge at the bottom? That is something that I would like to regard afterwards via the add-on building model. Similar, and that brings us to the missing walls, because in between those two blocks, so there's one area here and one area on the other side that I'm not modeling right now. And in between there should be some fire resistance wall, for example. So here we define a wall and maybe make a new one, and maybe the first one should also be a layer, but I would like to use the same producer, not that thick, because a wall does not have to be that thick as a floor. In here, let's say we put it from this into up to this point, right? So that's there, and then in the last matter we would also use a timber frame wall in here. Therefore, well, just for showing what is possible with it, we use therefore the thickness type beam panel, and I have a predefined beam panel here with 240 millimeter thick C24 material. So that's all arranged. It's stapled with some connector spacing, and I have also defined sheetings in it. So the one side is planked with OSB and the other one is planked with some gypsum fiber material. So that's also there. All right. And I would like to define it from, let's say, from this area to this one, because I would like to have then afterwards a little gap there in between what I can make just by editing the mode and defining it to 2.4 meters. In that case, I'm avoiding connection issues between those layers. So that's all there. Okay, so another thing that I need to do there is to define some opening. And well, I'm not making too much essential structure. I hope I said it already. I would not regard any or take detailed explanation to coupling or other effects here in the structure, but I probably want to at least define an opening here on the bottom. Therefore, I will probably divide the middle line by 2 intermediate nodes, right? And then this length is a little bit too long. Let's say we make here minus 6.2. Well, that's too much. That was too much. Hold on. So then let's say minus 6 meters. Also still too much. And then we can actually maybe grab this one. So that's minus 6. So that's directly on the center. That's not what we want. So we want here minus 5.75. Makes sense to orient a little bit before we put lengths. We have 1 meter, so we say minus 4.4. So to me that's good to go. 1 meter 35, and I will copy this one. Just one copy by minus 2.25 meters, and that helps me to arrange the opening numbers. So take a look at the rendering. Oops, that's good. And then we can just take the opening. Maybe with this one, I'm not so sure. And copy it 17 times. That's one story we have already by minus 3 meter. Right. And I would like to intersect the lines already, because it's just helpful in this matter. So here, that's done. All right, support. To switch off the visibility mode. Maybe before we define the support, just so that you know, here's the timber frame wall together with all the couplings and the sheetings generated inside. That's one part of the issue. Okay, we go to support step. Okay, line support. I will just fix them. Oops, no, that's too much. I think where I wanted it. And I want them to this line this line. That's good. And this line. This line. This line. This line. This line. Right. Again, all right. Minimize that also. And then that brings me to the nodal supports. Underneath here, so there's one supported this one. This one. Well, all of the columns should be supported. This is this. This one. Too big. Okay. Good. So centers there. That looks quite good. We can have a little check by generating or displaying the mesh. And so just we know that everything is modeled correctly before we put the loading on it and also mirror it. So it looks good. We do not see a mesh here. Why it does? Because we have not displayed the timber frame wall on it. But here it is. And loading we put on top of it. So we go in fly mode again. And what load we want to have on it is 3.4 kilonewton per square meter. There. And that should be this. No, this one not. Red one. From left to right. Okay. Okay, so the load is now assigned to all the stories here. Okay, a little bit also on this ones. On the small ones here. That is maybe something we can delete. Because we don't want to work it as that. Changing the result too much, but yeah, we just don't want it. And now we go to fly mode again. Then display the floors, and then we will skip this one. This, so we will hide the selected objects, and then we can put also the 3.4 kilonewton per square meters to all surfaces here. So looks also good. Cancel the visibility mode again, go back to fly mode. And then mirror it, create a copy in the Y, Z direction on the origin. Okay. So the structure is there and it's all generated. We can, as the modeling process is solved already, we can switch off the grid and take a first look at the results. Yeah, I think I said it, but just to focus on it again, this is missing the columns in this point, and also in this point. And so I expect quite a high loading in here. And when we switch off the force and maybe show the building model again, or the center of mass. So we have 34 tons in each story. That's all the same. In here, and I expect quite a high loading, or the center load I expect actually in this area here. All right, so then the calculation is done, and you see that the structure is, well, deforming a little bit into the front, like a little bit out of plane, but that's not the main interest I want to focus now on. I will maybe like to switch off the mesh. That's not the interest, because before we are analyzing the 3D effects, I want to mention the options or the informations that I have now together with the definitions of the stories here. You know, if you remember, in the beginning, where I introduced it, I told you that we have the floor diaphragm none, so we use the original stiffness out of the area. We have that for every story in here. So now what do we have with the information none in here? So we have the center of mass and rigidity. We have it once again for each story from 0 to 17. We have for the load case that we have calculated in this case, we have the story action, so we can see what force is applying in horizontal direction. So all the stiffening elements, okay, we do not have wind load or earthquake load in here, but imagine we have defined it or arranged it. It would give us the information, this horizontal force is transported in X direction. How much mass do I have to activate in here? And we have the deformation of each story. One thing that I forgot and what would have also given me additional information is that in the building model add-on here, I have the option to define floor sets, or floor sets are already predefined when I'm defining rigid or semi-rigid. I will show that afterwards. But here I can define deep beams and shear walls. And for shear walls, I want to define them just on special points of the structure. Therefore, I go inside and define one new shear wall, and which one do we go back to the fly mode, of course, switch off the results and say, okay, I want this. So, well, maybe we will use all of this. That can be quite ambitious, I have to admit, that would be possible. Define that here. And now we can generate result sections, which is now for our purposes not so important, but just to mention it, it is the option to also have in each story for each wall a result section. But there's also will be generated a result beam or a result member in each story, and that actually gives me also this information. So maybe I will just do it for one side and then we can show the difference. That would be easy. But the important thing that I would like to mention is here the design properties. Because now, of course, on such a structure, you would probably for the center or the stiffening center that you have in the structure, you want to model or to verify in the static analysis also buckling of it. And that can be done in here with not a surface anymore, but with the result beam that is defined in here. And that's, yeah, quite a good information you can have. It's a simplified verification, but it's a very quick verification that you can do with it. Okay, so you see here, right now we have the complete story, but once again, we will not have or analyze the design completely of it. I will just want to show you what informations you can gain from the building model add-on. Okay, so that's the first information that you are important, the benefit that you can get from the add-on building model. So, okay, reinforcement, that is actually all the same that we have for other concrete structures. But here in ultimate configurations, in the design configurations for the concrete, you have for the, just let me look. Here, let's see. Now I can detailing and particular routes for deep beams from building model add-on. Okay, deep beams we do not concentrate on today, but here just below we have detailing and particular routes for shear walls from building model add-on, and it will automatically, from the definitions that I have in the building model, generate the orthogonal or transverse reinforcement according to the Eurocode in this matter, or to any standard that I have chosen in here. So that's quite an important information that I can also give the software. Okay, that is actually all. Okay, of course, it's deleting my result. That's why I should have probably defined it before this, but okay, so we will do it on the other side, and on this we will not even regard the design properties and also not the result section, so it will just give me the result beam in there. And we also have timber frame walls and CLT walls in here, and that makes also sense to define here shear walls inside. So we will select a timber frame wall in here. That will not give me, oh my god, because it's then always conflicting with this. That will not give me benefit for the design properties in it, but it can give me a complete shear force that's coming through this wall. I will show that on this afterwards. And for CLT, I will have actually a benefit of it, and that I want to show also. Right? So, and for this, I have now the section of the wall. Here, 140 by 2500. And I have here, similar to what we've had for the concrete, the option to define the effective lengths. Okay, lateral torsional buckling is something quite special. We probably do not want to regard this, but what we probably can do is do a buckling verification for the minor axis out of plane area. And it's supported in each story. And of course, okay, we can maybe add the intermediate nodes and just activate them all. That's also possible, but we can also just simplify it. Use the minimalizing of the length. So this is possible. So let me just show that here. And now it's supported, and I'm calculating with beta, the effective buckling factor beta equals 1 inside it, and do a simplified verification of this. I will directly jump back into this just before I missed, or I forgot also one thing to regard, and that is the stiffness orientation of the CLT, which is also important. So here under, let me think, surfaces, in the display navigator, I have layer directions that I can activate, and I can have the resultant of it. And so you see that this is, if we imagine that there is the column here, that's wrong from the stiffness orientation, because when we just take a look to the, and now we have to maybe keep a little detailed look into it. You see that the layers are oriented with the top and bottom plate, which gives you the main stiffness direction in global X. And that's wrong, because you don't want to orient it that way. And we also need to look for the walls. They are also oriented wrong in here. So when we look for these ones, you see, yeah, to show that again, there's top and bottom layers of it with 40 millimeters in thickness. And if we have oriented in this or span the CLT plate in this direction, you would have an enormous settling in the structure, which is, yeah, then something similar what you have when you are modeling a log home, like 20, 30 centimeters or more in such a high building. So that's not what you want. And we have to change it, and therefore activate those surfaces, these ones, as similar to these ones, and say right click and surfaces, edit. And I have here a specific axis that I can orient. So that's rotated by 90 degrees. And I hope now the stiffness orientation is changing. That is changing. So that's perfect. And when we look for the other one, also this. Oh, it's not visible so nicely, but maybe when we just display just this one. So that's quite nice. That's what we want. It's oriented vertical. Okay, cancel the visibility mode again. Maybe when we are here, switch off the reinforcement. I said it already, we are not interested in this today. All right. This, let me think about, I'm not so sure, but we probably will take a look again. Okay, so now we have calculated again. It has this additional shear walls that I had defined are not giving any stiffness to the structure. It's just for the design of it. And what I have also, I have here now from this information 2 additional columns. So I have the forces and the shear walls, and that's what I actually meant when I started. When we maybe go back to fly mode and select just the timber frame walls, visibility by these ones, and when we just display them. Okay, once again, we do not have horizontal force, but you can see that you have for each one the horizontal force, and this is an important information for the timber frame wall. We have, when we switch on the result of it, there's a result beam that's also showing me the horizontal force just in the timber frame wall. Or in this case, the normal force, but when I switch it here, it's showing me this force also. There's also already a little indicator about problems, but before we mention the problems, I have to show you also the other option that you can have. So now the CLT wall, when you do the CLT analysis of this just one wall that we have here in the front of this. So I know it's very good to see, but yeah, this one, this one, this one, and this one. And what you could do now is that you go into the timber design and say, okay, I'm doing analysis for this CLT surfaces, for the floor and also for the walls. But there is an issue with it because the surfaces itself, they do not have any buckling verification in it. So when we go in here and then you have here design types, configurations, you see there's no stability that you can define. When you compare that with the column here, there, when you go to design types, you have effective lengths. And now how can the building model add-on help you with this? Quite simple, because when we go to the shear walls, you just have to find the right one. This is this one. You can say, okay, I have here this, and it's generating me a result beam. And now, ta-ta, surprise, here you have effective lengths. But the problem is, this is now for a width of 14 centimeters. And when you take a detailed look, 14 centimeters is not really correct, because I have here middle layers of at least 4 centimeters that I need to eliminate from the stiffness, because they are oriented into the other direction, and in vertical direction they have a very, very low stiffness, at least theoretically. And now how do you have to regard that, or how can you regard that as an option? You can go into the shear wall, edit the cross section, open the air section add-on. Sadly, it's opening on the other screen, but I will directly, when it's opened, move it to here. All right, so there it is. And now I can say, I said it already, well, the truth is somewhere in the middle between 10 centimeters and 14 centimeters. Just to be on safe side, I can calculate it with, or define it with 10 centimeters. Say save and return. So now that's saved, and you see that I modified the structure in here. And now, okay, one thing I forgot. I also have to define here timber with C24 grade, just as isotropic material, and press OK. And now I can do a buckling stability analysis together with the stress analysis from the add-on timber design in here. So that's, yeah, quite a big benefit that the software will give you, or that the add-on building model, it's not typically software, it's just the add-on can give you. Okay. Okay, so this is the design options, or the additional information that the add-on building model can generate. Now we want to take a look, or more detailed look, in the problems that are occurring with this. And therefore we take a look at the normal forces. Now for the center, we will switch to the results here and take a look at the center normal force, or the force in the center of the column. Maybe we go back to my beloved fly mode, and we'll just display the center force. And now you see that I have here a normal force in the top story of 18.26 kilonewton pressure. And of course, in each story is coming more normal force, so that looks quite all right. But one will say I have quite a high loading of 3.4 kilonewton per square meter. And I don't want to recalculate that now on detail, but I have also a very high self-weight or a mass in the center of 34 tons. So 18 for the center column, that probably is too low in here. And why is this occurring? The reason is that the structure itself, and maybe we can go out of this one node in here, is like completely settling. Yeah, well, I have modeled the complete structure and calculated with just one finger snap. But that's not how such a building or how the loading behavior of such a structure will work. Because how will such a story be assembled? And that is, maybe we go out of the results and just look for the stories again. In here, just display the first and the second. So the first one is assembled, then the structure is settling at least a little bit. There's also a strain on it, so maybe we bring the display results in here. So you see we have the strain on it, but that is the complete strain of the whole structure, and so it's kind of tying, or the force in the top store is moving away from it. So the strain is wrong, and also the normal force caused by this is wrong. And that is an effect that's coming from, or that's occurring in higher buildings. Okay, so how can you regard that? Several options how to do it. One option is to go into the building model add-on, double click, select all the stories, hold on, and then say, okay, I'm using the floor diaphragm semi-rigid in here. Okay, there's not changing that much on it. Oh, hold on, I forgot one thing. Yeah, of course I want to continue, but I forgot to show the other effects. Hold on, so here, now that I've activated the floor diaphragm semi-rigid, I can add a nodal support modeling in here. So via the drop down, I have now the option to say, okay, give me an elastic behavior of the column. So each column will now deform. What is done now, and what we can see when we maybe switch just the calculation on already, that now here you see selected for calculation, load transferring, so it's dividing a little bit the load. That's what it's done. But here's generating the mesh. And here's the first pre-calculation for the calculation. But after this is now done a separation into, well, 2 or 3 steps. It's, you can see that how you like. The structure is separated. Here you see, so there's the static analysis and the floor analysis. And what I call it a 2.5D analysis in it. So it's calculating the floor as just a position analysis static, and then separately in another model it's calculating the walls, and that gives you the benefit to calculate separately and still work with several positions. I will show that once we have the results, because then it's probably better visible what's coming out of it. So now that we've calculated it, we have here analysis of a building story, and we have here global deformation for the walls, that's not so fancy, I would like to say. But here you see that in here for floors, it's only calculating the vertical, sorry, not the vertical, only the horizontal elements. So that's this concrete surface and the CLT. The columns here are not really existing. They are skipped out of the 3D model. And maybe we go to loads from transfer surface and show that again. So then go like this. And you see there's a force of 3.4 kilonewton per square meter on it. And we define loads from transfer load surface. You see that the load is from the first story is summarized here in this and transferred to the other. Right? And this will then also regard the settling that I just defined via this option that we had. Maybe we can display it again. Via this nodal support modeling that I have. So what effect do we get from this? Yeah, of course, now the complete structure can deform, and the settling or the settling that's occurring during the assembling of it, the 3D effects are harmonized, or however you call it. And when we take a look at the normal force right now, and then of course go to walls and floors, you can see that here we have near 30 kilonewton, which is something that I would have expected. The value that I had there before was just wrong. And why was this wrong? Because the strain of it was also wrong. When we look for the strain right now, you see that it's just much better, yeah, harmonized of it. All right. Maybe go back to the first entry of the global 3D calculation. What is, and show also the deformation. What is done with semi-rigid here in this area is that it's calculating the in-plane area, so the CLT wall in here, and it's, when we take a look at the stiffness matrix of it, just for your imagination, it's defining all these elements, bending, torsional, stiffness element, to a value near 0, also the shear stiffness, and only this membrane stiffness elements are activating in semi-rigid. Okay, so this is how you can regard 3D effects, and the content of today's webinar is not only 3D effects, but also problems that are occurring in 2D design. And a lot of customers are using or still using 2D design and not concentrating on such effects. And therefore I have prepared a short demo. I will just fly that in. So this is the 2D analysis of this structure. So kind of, well, drafted out of it. So it's similar loaded, and you see here that I have the effects that I did model with the column supports here via edit node. Here stiffness via fixtures column. So it has regarded the dimensions of the column underneath, 30 by 30 meters, and also the column height. And from this did generate a slip. So, and when we calculate this one now with the same load, of course, you can see now that the load transfer or the vertical force of it, we'll be able to see that when we get rid of the mesh. and get out of this rendering for the center. So you see here, not so good to see, but maybe we do it similar for what we did before, just show this one. So it's 28.9, which is the same value that we had here for the center column. And that's the point where we're looking at. And of course, it's the same vertical force because that is the model that's in the back of this, as when you define this load transfer type, semi-rigid or rigid in this case. And yeah, it may be what is better even to show on this structure is what effects are coming when you are just calculated by one finger snap, which is once again wrong. And therefore, what we could do is first we go rid of the results. We will delete them anyway, and just display this one object. Delete the support there. And define here the column underneath. Well, we would need the bottom. Okay, okay, perfect. And we will maybe define the same section. So you got 30. Well, it could have hinges. Also, we have this one. Okay, so that's not so important. Okay, we'll just leave this out of it and say all right. And all right. And that should be right. Yeah, okay. The hinges are not the important point of it right now. We would like to look for the normal force. It's not supported. Sorry. That makes no sense. Of course, we cannot define the columns. We also need a support underneath it. And then we make nodal support underneath this. So here's the new nodal support. And it should be around this node. Okay. Okay. So now it's supported. However, did not else up. Okay, and now it's giving me quite a high support, but that's not what I want to look for. I want to take a look on the internal force and the normal force, and you see, okay, that's the same structure. It has the same loading, but it only has a normal force of 3. And why is this effect occurring here? Because it's all calculated in one sudden issue. And there you see the strain here is way too low of it. And that's why this is just a completely wrong result that I got out of it. And if you then change this one beam to a rigid one, calculate again, you will not get any strain out of it because it's the effect. You see, so we have to switch that here for numbers. And you see, we are back on the track, back to 29. Why is this now a better result? Yeah, of course, I do not have any strain on it. It's an extreme example, but of course, that's how it's done. And we can also just, lastly, take look to the what's happening when you maybe just calculate one story of this selected object and then take a look at this one and what's actually the problem when you are doing 2D analysis and not concentrate on such problems. In the bottom story, that will just give you this wrong result of 7%. Right now, when we just look for one story of this, and look for the downfalls, of course, that's good in here. But when you put that to the bottom and to the 17th store, to the 16th, and so on, then, and you have this always not movable, not regarding any spring, then you would get this very low value that I just showed on the beginning. I've made another just for explaining the importance of this. I made another structure with this so-called load generator on it. I also don't want to use too many words on this, but what you can do is to calculate every story as a 2D model and summarize them in our Dlubal center. And then it's possible to transfer the load from the, for example, from the 18th story. So that's the top story. Then here it's with the settling 28.9. So all this stuff is in there. And then go to the story underneath it and say, okay, the connected model is 18. So the 18th story. What supported nodes do I have in the other model? What loading do I'm getting there? And now when we switch off this and calculate it, it's keeping the informations or the support forces from the other model with the, was it 28.9 kilonewton? So, and now you see, I have the result, just have 1 minute, something down. And when we look for the forces, you have here the 28.9, which is maybe when we tile it in this way, you see here 28.9. So it's taking the force from this node and applying it on this. And then, of course, together with the other load that I have in here, it's giving me this 57, which is also the normal force. So that's a way how to regard also 3D effects in 2D. But of course, probably everyone will agree that it's quite a lot of work to model something like this separately and then connect it. So it's probably, if I had a choice, I always would like to stick on something in 3D where I have options that is giving me 2D results in a 3D building and regarding 3D effects and selling effects and so on. Okay, so this is now done, and probably we would like to add now the center column or the missing centered column on this. So we one more time go into the fly mode, define the column with this, what, and it's okay, there, it's of course there, and there. It's now supported. So to do this. All right. And here. All right. Okay, so this we could now calculate it with the semi-rigid stiffness again, but I don't think it's so much interest because I want to show you also the floor diaphragm rigid. And here the rest I leave all the same, but when we put on the rendering, you see that by defining the floor diaphragm rigid, you see this, well, little red dotted lines in here. Right? So the difference, I mentioned it already, from semi-rigid to rigid is that now it has a very high stiffness in the area. There's not any more the stiffness that is calculated here. So, but each FE element is connected to the mass center with a rigid member, which has hinges on its end. And we can also calculate this and take a look. So the settling effects is all the same. And here you see for the normal force. You know, when we go to the walls again, and we see that I have here, I've added this column here, and now the load, of course, is transferred more. Okay, this is the effect of, or the options that you can have from the add-on building model. And that brings us to the add-on construction stages analysis, which is another option for regarding such effects. And it has also more options when the structure is unsymmetric. You have failing members, creeping, for example, something we did not really mention today. This is all possible then via construction stages analysis. So this goes much further than the options that we have in the building model right now. I will also switch off. Not matter that much. No, we don't need the information anymore, and I don't actually want the little dashed lines here. I could just switch them off also, but it's important. Before we go into the add-on construction stages analysis, I would like to change this. Oops. We need to change this surface. Yeah. Just because I want to simplify it a little bit and make that all a complete CLT plate. It's just a simpler definition. Oh, okay, but maybe we'll arrange it also vertical. That time we should take. Or maybe not. Actually, why don't we want to look at the settling and look for the definitions? Let's write it down. Okay. Okay, building construction stages. So we say new construction stages, and I said it already, with this add-on, you can regard construction stages and failing members and all this stuff. How do we do that? We will activate the member surfaces nodes for the line supports in the first step. Go in here and say add members. We go into not in that direction, in this direction, and say, okay, give me from left to right. So give me all the members that are in the ground floor. Surfaces, I do it the same way. Also, all right. And model support, I can actually simplify it and say all. And then I'm defining the second stage with model support, so then not important because they are already there. And I just add these members and these surfaces. Okay. Now that's done. And I would also have to do that now 60 more times because, of course, my structure has 18 stories. So here's the first one. Go to the rendering, and here's the second one, and so on. That is something, I don't know how you feel it, but to me, it's something I don't want to do. And this is something I want to let the artificial intelligence do for me. But before we go to this definition of the construction stage, we would have to add some load in here. There are other options how to regard it when you have combinations. You could also add consider construction stages there with it, but yeah, once again, we do not do any detailed design of it today. We just do analyze 3D and 2D effects, and therefore we say all right and calculate the second story or the second construction stage. Okay. Yeah, we do not have the center now anymore, but you see that this and the normal force, which is quite similar, I have here this deformation. We can take a look at the first stage, and yeah, so this is settling, and then additionally to the existing deformation is coming this other deformation, and also the strain. The strain is something more and more interesting. We can also take a look. So it's going to see this and this. It's coming. Okay. Yep. So I said it already, something that I myself don't want to do manually. That's something I want to let the AI do for me. And therefore, so let me just open some internet browser and type there .com, and now I tell it to please generate the next 6 stories. Model, and as a hint, flows to model construction stages. Missing 16 stages. All of the first 2 construction stages are already defined. 16 more needs to be generated for each story. They should look the second construction stage, because in that way I do I do miss the, how you call it, I do not let it generate the supports and the normal supports. That's one of the issues. I gave it also a little prompt just so that it remembers. Usually now it is connecting to FM via the programming API, application programming interface, and we'll hopefully start to generate stories. And you can see, in fact, the 18 construction stages are defined. Looking for final verification. Okay, so yeah, the construction stages are all generated. It offers me also to calculate them. Now, if you want to have more interest, if you are interested more into this artificial intelligence, we offer, just give us a note. It's an addition, and once again, should not be part of this webinar, but I think it's a good way to generate such things that can be quite annoying, and probably, I mentioned already, we don't want to select, go inside here and go to first register, second register, and so on, and calculate it. Okay, first and second story construction stage we had already calculated. We let it now calculate all the construction stage. Take a look on it. I expect probably now in the top story the real big difference to the building model add-on. At least not difference to the building model, which is regarding the settling, which is correct. That's correct. But with the better normal force. Okay, so and now let's take a look at the normal force again, because that's probably the point where we are hanging on, and you see, so that's quite similar to what we had before. Take a look at the strain in this. So you see on the top story 0.03 and on the bottom 0.18. And what's maybe interesting, maybe that's probably very interesting. If we go now, remember this strain and go for the first story. No surprise, but the strain here is similar to what we have in the top story in the 18th building, and it actually will be the same with all the others. And one of the nice things with the construction stages analysis is that you can now kind of drive through all the areas of the complete building. And then you look for the support forces to see how they go up in each story that you are putting on top of it. Okay, well, thank you very much for your interest. I think it's quite an interesting topic, how to take care, and I will give back the word to my colleague Andreas. Thank you.
Thank you, Bastian, for your presentation. At the end of the webinar, I have additional hints, for example, to our online courses. Where's the FM6 course? That's a course for beginners. Then the Eurocode 2 course for the concrete design with FM6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. The Eurocode 8 course for the earthquake design. And the AI Masterclass course. for the application of AI. You can get an RFEM course or a neural code course for free when you submit your customer project, and when we publish it on our website. Courses are valued at 199 to 399 euro. Just click the link here or scan the QR code, and there's a page, a form page, where you can upload your files. You can also write me an email to info@dlubal.com, and I will answer you and write what files I need. Then there are our free online services, for example, the Dlubal community. You can ask questions there, and our team or our users will answer you. Then there's the geozone tool for the determination of wind, snow, and earthquake loads. You can determine cross-section properties. Then you can download 3D models, for example, as a template for your project. Then you can download the free trial version of RFEM 6, for example, or R 9, R-Wind 3, or R section. They are valid for 90 days. You can find more information on our website, dlubal.com, for example, the recorded webinars, then, for example, knowledge base articles. You can ask our AI assistant, Mia, 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again to Bastian for your presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.